Hello, in this video we're going to be talking about particle in a box in 2 dimensions and 3 dimensions, and particularly we're going to be discussing degeneracy in terms of symmetry. Last time we discussed that in terms of energy, and we looked at energy diagrams, and we also made mention about the 0-point energy for the corresponding 2-dimensional, 3-dimensional problem. So let's look at that from the point of view of symmetry. What do I mean by that? So in this case, we just know that these two states, for example, have the same energy. When we refer to symmetry, we actually have to look at the wave functions, because once you plot the wave functions, you will see that they are effectively two different states. They're not the same, but they are related by symmetry. What does that mean? If you start with this state, nx2 and y1, if you rotate it counterclockwise 90 degrees, you get the state nx1 and y2. And vice versa. If you start with this state on the right, rotation clockwise 90 degrees will get you to this state on the left. And here, those are projections, contour plots, projections in 2 dimensions of our 3-dimensional plots that we have in here. Both of those states will give you 5 times this amount of energy. Remember, all of those are constant values. So how do we do that in Mathematica? Okay, so let's bring Mathematica. We remember that we are looking at states where the length of each of those directions of my box are equal to one another and equal to a fixed value. So we have either a square region or a cubic region, depending if you're doing a 2-dimensional, 3-dimensional problem. I'm defining those values in here. Lx equals Ly equals to L. I'm giving it a 3 units. This could be 3 nanometers, 3 picometers, whatever. You can change them accordingly to your problem. But for now, this is not going to change any of the results. When you define your wave function, which, by the way, here I'm defining in terms of 2 variables, it's going to take 2 parameters, and those are going to be the quantum numbers in the x direction and the y direction. I'm here making this expression the most general possible, just in case you decide to use this expression. For the most general case where this Lx is different from Ly, is still taken into account if you set up your equation this way. So let's just test it very quickly. Let's give the first principal quantum number in x equals 1, quantum number in y equals 2, and then this is the way that we actually fit in those parameters into my wave function. Remember, the wave function expects values for those 2 parameters. You can express them this way, or you can literally come and give it values for 1 and 2, but I will advise you to do it this way. Anyhow, those 2 different ways to input your answer. So this is the wave function that you get with these values that we have provided. How do we get my plots in 2 dimensions, or in 3 dimensions? For that, we're going to be using the function plot 3D. That, remember, in Mathematica, you can actually have more information by just expanding the help menu. But in this case, it's very similar to what we have before for just the regular plot function. Still, I have to plot 3D my function, then the interval for x, and then the interval for y. Now, I am using this extra function just to give labels to my plot. You can either leave or put that in, but this is going to give you the liberty of putting whatever labels you get on your axis. One thing that is also useful in this type of graphs is that you can rotate them once you generate them, and then you can actually see some of the features in the 3-dimensional plot that you're getting. One thing that I want to point out in this case is that you can see clearly by rotating the presence of nodes. Remember, nodes are those where your wave function goes to a positive to a negative value, has to cross 0, and that crossing of 0 is what it's characterized as a node. In this case, though, since you are having wave functions in 2 dimensions, those nodes are not going to be points, but are going to be lines in that xy plane. And you can see that in here. I'm going to suggest you also to use a different type of plot. Like in this case, it's just plot 3D, but adding these options just to characterize the mesh that you are putting into your function, that it's some visual clue to help you out having the depth or the shape of your 3-dimensional surface. But in this case, once we did this, you add these options for mesh, and what it's going to be doing is creating contours or slices of your 3-dimensional plot. Now you can clearly see again that you go from bottom to a peak or from near 0 to a valley. Now you see that crossing from positive to negative values through 0. Now in this plot is very clear that this whole line is your node. Again, not a point, but a line, since we have a xy plane. The features, you can rotate them, you can see very clearly positive and negative. There's a third way to make these plots, which is basically this projection that we are doing by moving the graph. Mathematica can do it for us by using the function contour plot. And very similar to that, it's contour plot your function with specified values, and then your ranges for x and y. Again, we're just putting this frame label in order to put labels for my axis x and y. Not necessary, but useful. So when you do this, this is exactly the projection that you will get by moving this 3-dimensional object to the corresponding position. It's a projection where you are looking at your plot from the top. So you have that. The colors also represent the fact that one of them is going to positive values, the other one is going to negative values. And you can also see that by just coming into your plot. Every one of those slices have a value associated to that. So this tells you that this region is going to a peak, sorry, a valley, because it goes to negative values, whereas this region, since each of those slices go to positive values, this is representing a peak. And from top to bottom, you have your node. Okay, so now let's look at the degenerate state, nx equals 2 and y equals 1. Same ideas, same type of plots, just different options, and this is what I mentioned before. If you change the values from the top, you don't have to go and change manually each of those places where you define your function. Otherwise, if you define it manually, you will have to go and change every one of this, a pain if you have more than a few instances of writing your wave function. So you change your values, and then these 3 different plots, now you get these other representations. They are very similar to what we had before, of course, because it's a degenerate state. They are related to one another by rotations. And again, this idea that you can have this 3-dimensional plot that you can rotate in real time, that gives you a very good tool to say, oh yeah, this state, when I've rotated 90 degrees clockwise or counterclockwise, gives me one state or the other. Okay, you can explore that rotation on your own, but it's very easy to see once you have these 3-dimensional plots. The contour plot is going to give you same as before, but you can clearly see now that they are related to one another by that symmetry. Another useful tool that I can suggest you to use is the function grid, where the only thing that we're doing is plotting each of those wave functions side by side. And then it's much easier to compare how they are related by symmetry. You're not only restricted to do 2, 1 and 1, 2 combinations, but let's say, for example, that you were to say, well, what about 2, 2 values for the quantum numbers x in y and x and y directions? And you will see that in this case, it is exactly the same wave function. These are not 2 different states that are related by symmetry. Those are indeed the same state. The wave function tells you that. It is exactly the same, no difference between them. Whereas these ones, clearly they're not the same, but related by rotation. And yet another function that could be useful is the function table that I'm putting here. You can see that in general, what I'm doing is do a contour plot of my wave function, and I'm just adding these other options for color function. I'm just changing the default color to rainbow color, and I'm actually giving the x and y labels to the axis. Now, in this case, another thing that I wanted to point out is that whatever values you're feeding to your wave function, as long as there are 2 different values, it's going to be okay. They don't have to be any specific labels. Those are just labels. In this case, I changed from nx and y to a and b, and those a and b are running numbers from 1 to 3 in each of those cases. I will suggest you to do something that is related to the property that you are plotting, but again, just labels. And now with this table, you are creating a series of plots that then you can analyze because now you have this wealth of information, not just restricted to one value or plotting one at a time. And the options that I'm giving you here is just for you to read, but basically the idea that I'm having in here is that all the results that are created with table, I put them in a specific arrangement so they just look nice and it's easier to read. Not necessary, but it'll be useful. So I leave you with those options that you can try. The result is this table that is generated into this grid where I have nx in rows. So that'll be nx equals 1, the second row nx equals 2, and so on. And columns are representing ny, the principal quantum number in the y direction. So by looking at those combinations, you can immediately see that when the quantum numbers are the same, you don't have any degeneracies. It's all the same state. And this is represented in this grid in the diagonal of your grid, 1, 1, 2 with 2. Those are unique states because they don't have any other state in the grid that is related to each of them. But if you go, for example, 1 with 2, there's a state that is related by rotation with, which will be the state 2, 1. So you can see these 2 states, yes, they are related. If you go to 3, 3, 1, and 1, 3, they will be related also by symmetry and so on. Okay, so there's a wealth of information that you can get by using this table function where you're creating multiple plots at a time, and then you can start looking at the features that are involved. You can immediately see in these cases is the nodes with contour plots, and that's why I chose to plot it this way instead of a 3-dimensional. In this case, looking at the nodes, it's much easier with the contour plots. This one will have only one node. This one doesn't have any nodes. This one will have one node in this direction, one node in this other direction. This one has one node, 1 and 2 nodes in this direction, 1 node in this direction, and so on. So every single one of those lines, remember, since you have a plane, those lines are representing nodes. You have 1, 2 nodes in the x direction, you have only 1 node in the y direction, and so on. So there's a lot of information that you can actually get by plotting multiple plots in just one side by side. Okay, I hope this is helpful. Let me know if you have any questions, and I'll talk to you later.